yeah, so this is my second recording. Unfortunately, all the video was lost due to I didn't start any audio recording. So today I'm training a new AI model for predicting stock market movements, which is just a fun project to see and learn like how much of the movements can you actually predict and how difficult is it to predict them. Can you just put something simple together, or do you need something very complicated to know? And so this is the second software. The first one was a bit more chaotic because there was more moving parts and I was trying different things. This one is a bit simpler, that's why it's called Finance Minimal, which doesn't mean it's minimal, it means I'm trying to make it minimal. So you can see the code running right now, and it's training on a dataset that was downloaded from Yahoo Finance. And so this is the second version of the code. It has pretty much a standalone functionality. Almost everything needed is in this code, and it's around 700 lines of code. But it's a lot in this code, so it's quite compact still. I'm using a RAM loader system, which is going to fill up a certain amount of gigabytes. Right now I'm just doing 0.1, which is around maybe a few hundred stocks, just to try the model and see how the correlations are in the validation data. And it seems to, we'll get into that later. So the RAM loader will load in a certain amount of stocks from the disk, the hard drive, into the memory, and this is going to make it much faster. So when we're feeding it to the AI model and randomly sampling from it, it's going to go much faster than if we did it from the disk. And so this will use many threads many processes actually to fill up the RAM, and then when it's filled, it's going to just be like a good service to us and give us the data when we need it. Through this function, we just say when is our cutoff. We want from the start, like 2000s to 2020 is the training, and then validation is 2020 to 2022, and then 2022 to 2025 is the testing data. And the data type, you can specify which one of these three segments you want. And this is just a simple approach. There's better ways to do it. You could do cross-validation of the different time periods, like training on recent data, testing on previous, and etc. etc. But this works for now, and it's a simple way to do it. Max retries is just if you can't find a series, you retry. If there's for some reason the particular stock that you chose doesn't have enough data, or doesn't have enough data in a certain period, then you retry 50 times. But usually it doesn't need to be that many times. It's usually going to find it in one most often, or maximum 2 cases. So this could actually be a lot smaller. I might even change this right now. Anyways, so this RAM loader is a very convenient function. I tried different methods, and this seemed to work pretty quick. As you can see, it's gathering around 500 stock series per second, I think, because the batches are coming in like 2 times a second. So maybe 250 to 500 time series it loads per second, and they're 270 steps long. So I guess it's I don't know if it's too slow or fast. I would say there's probably many ways to do this much faster. Probably you could write some optimized C code that will just blast out the data faster than you can think about it. And this is probably ridiculously slow compared to that. But that could be a future project actually. Then I'm just gonna check at the time. Yeah, so this is just a small class that will basically interface with the RAM loader, and it's just gonna get batches. So it's gonna, one single process is gonna get the batches, process the data from the raw format to like a stationary log1p transformed version, and that's for basically making it easier, I think, for the AI to understand the data, because log1p series you can just you can sum all the days together, and then the sum is going to represent the change from the first day to the last. Whereas if you have the normal and not the log1p change differences, then you have to multiply. So it's 5% up, you have to multiply each one. And I guess it's easier for a neural network to understand summation, because that's the operation it works on. Matrix multiplications are summations, so probably that's easier for the AI to work with, and that's the reasoning behind the choice. Probably it would be a good thing to do empirical comparisons as well, and that could also be a future project. So this is the model. It has 3 convolutional base layers and then some linear layers. And the convolutions is basically mostly to filter out noise, or try to filter out noise, and capture some interesting features, and process using that part, and then some linear processing. And I found that through experimentation that it doesn't seem to work well to have multiple layers, unless you add residual connections and also normalization, because I think otherwise the data is lost somehow through the layers, and it takes a very long time for it to reach even baseline level of prediction ability. But with this it can reach much faster, at least some level of prediction. It's quite small, but it's still I think statistically significant. I didn't try this particular one, but I tried other versions. And it's mostly random noise on the stock market, but there seems to be some patterns you can predict. And here's the main training loop. It's gonna create a model, load if I want to from a previously trained one. It's gonna do some epoch counting, and it has a while loop that just trains forever if I don't stop it. You specify the model dimensions, the sequence lengths you want. This is 3 months times 5, so it's 1.25 years. And you can see the parameter counts. It's around 200 megabytes, I think, which is much larger than it should be. But I think there's some overhead in the NVIDIA, and this is just a tenth of a gigabyte of data, so a few hundred stocks, maybe 700 or something. I don't know. And here's the fast fetcher based on the RAM loader. So and in the while loop this is gonna reload every time, and I think this shuffles as well. So it's basically loading 0.1 gigabytes, training a bunch of times, loading a new random sample of data, and then training. So it's just to speed up the training a bit. Probably there's better to do it in some optimized C library or something in the future. Anyways, here is the training part. You get the data sample and then check if it received anything, and then move it to the GPU and you predict with the model, and you have the predictions. The 0 column is the predicted movement, and then the next column would be the predicted volatility, which can be interesting to some applications. And it's not exactly the volatility, it's the volatility within the coming days, you could say. So it's the you can see how it's defined. Let's skip that for now. Wait, here, so here's the, you just take the standard deviation of the relative change. So if it goes up 5%, but then the days are like 5% and then 2% and then up 5%, then the standard deviation would be a few percent, I guess. And I think that's what we saw when it was printed. So it's basically just some indication of how volatile you can expect it to be. So some risk measure, basically, because you want the expectation and the spread of the distribution to get a more full picture than just the expectation. And then I use mean absolute error, L1 loss, which might seem like an odd choice, but it might be an odd choice, might even be better with MSE. But the reasoning behind this, I wanted the model to be more courageous when predicting regressions. So for example, if it predicts up and it goes down, then it's not going to be punished too much. It's basically going to, I think, with this, follow a bit more the stock movements and not be punished for big errors. Well, MSE loss would make it a lot more cautious. And then for some extra robustness in the error, I add this. And I haven't empirically proven that it's more robust using this. This is just a rule of thumb kind of approach. And then we compute some correlations and add this to the logging. So we use NumPy for that. Then we have the 8 validation steps to get a picture of the validation at each time point. And this also saves some models and then saves the final model as a general base. And we recently got a new model, so I could do we're gonna have to wait for this to finish before saving, because otherwise it's not gonna update. So now you can see the validation, and when it starts 201, as you can see, it reloads the memory, the data. And surprisingly, it doesn't overfit. Even if you have just a few series, 560 stocks, then it doesn't overfit, which is quite surprising. So let's just save the model first. So for later use, we could even do an ensemble of these two later. But anyways, let's finish this quickly. So we save the model. Here we have some other functions, but basically it trains the model. And if we look here, we can see some results. So this is just some ChatGPT generated code to view the results, the log files that are created. And you can just press enter, shift enter, and then it's going to reload, which is quite convenient. So it's like a hacky dashboard kind of thing. and you can see here it looks as though the validation correlation actually does seem to overfit now. So it seems after about 100 epochs it starts to overfit a bit. So it used to be 15% correlation, but now it went down to around 10% correlation, while the training correlation seems to be lower, which is very weird. But it's increasing still. Both are still quite positive. The zero line is here, and this is 10%, 20%. So 15%. That would be, if we just calculate quickly, 15% to the power of 2. That would be an R² value of 2.25%. So basically you could, overall, on all of the stocks that are trained on the validation data, it would mean 98% of the movements of the stocks are basically random or hard to predict, while this model can capture 2% of the movements. So that's gives some clarity in how difficult the problem is. Generally, if you could think of this correlation as if one of them moves up 1 unit of change, then the other one's gonna on average move up 0.15 units of change. So we could investigate through another method to see if you picked out the best 10% of stocks, how much would they move up or down compared to the benchmark. And that's a topic for another video. So thank you for tuning in, and see you guys next time.